You're watching something that defies physics. March 14th, 2025. A colossal solar storm packing more energy than 1 billion nuclear bombs screams through space at 1.2 million miles per hour. Dead ahead in its path, 3I/Atlas. The enigmatic visitor from interstellar space. This should be a massacre. When solar storms hit comets, they tear them apart. Tails shred. Surfaces boil away. Trajectories twist. We've seen it happen dozens of times. But as the plasma wall slams into 3I/Atlas with apocalyptic force, your instruments show something impossible. The object doesn't fracture, doesn't evaporate, doesn't even wobble. It takes the hit like it's nothing like Earth's atmosphere shrugging off a raindrop. While Oumuamua vanished before we could catch it, and 2E/Borisov followed every rule in the book, 3I/Atlas is rewriting those rules in real time. And the storm that should have destroyed it, it just revealed something we were never meant to see. If you're ready to chase this mystery to its edge, go ahead and like this video, subscribe if cosmic puzzles keep you up at night. Drop a comment telling me where you're watching from, or what about the universe fascinates you most. Now settle in, let the night embrace you, and let's uncover what's really out there. Let me take you back to September 2nd, 2024. You're an astronomer at the Asteroid Terrestrial Impact Last Alert System, ATLAS for short, in Hawaii. It's 3:47 a.m, and you're doing what you've done 1,000 times before scanning the sky for near-Earth objects that might pose a threat. Your coffee's gone cold, your eyes are tired, and then a blip appears on your screen that makes your heart skip. At first, you think it's another asteroid, maybe a comet, but as you pull up the trajectory data, something's wrong. Deeply wrong. This object isn't following an elliptical orbit around the Sun like everything else in our solar system. It's moving on a hyperbolic path, the signature of something that came from somewhere else. You run the numbers again, and again, the velocity doesn't lie. This thing is travelling at 34 kilometers per second relative to the Sun. Far too fast to be gravitationally bound to our star. You're looking at only the third confirmed interstellar object in human history. You immediately flag it for follow-up observations. Within hours, telescopes across the globe swing toward this cosmic intruder. The Hubble Space Telescope, the James Webb, ground-based observatories from Chile to Spain. Everyone wants a piece of this discovery, because unlike Oumuamua, which we spotted on its way out of the solar system in 2017, giving us barely 2 months to study it before it vanished, 3I/Atlas is coming inbound. We have time, we have opportunity, we have a chance to actually understand what these interstellar visitors are made of. But here's where it gets interesting. As the data streams in over the following weeks, 3I/Atlas refuses to fit into any box we try to put it in. Its brightness fluctuates in ways that don't match a tumbling asteroid. Its spectral signature, the fingerprint of light that tells us what something's made of, shows compounds that shouldn't exist together. Silicates, yes. Water ice, expected. But also trace signatures of metals that typically don't survive in the radiation-blasted environment of interstellar space. Dr. Michelle Bannister from the University of Canterbury said it best in her preliminary report. Every time we think we understand this object, it does something that makes us question our instruments. The size estimates keep changing too. Initial observations suggest it's roughly 400 meters across, about 4 football fields end to end. But its albedo, the measure of how much light it reflects, is unusually high. Too high for a typical comet nucleus, too uniform for a rocky asteroid. It's as if someone polished the surface to a mirror shine, which nature doesn't do, not like this. Then there's the trajectory issue. You see, when something enters our solar system from interstellar space, we can trace its path backward to figure out where it came from. Oumuamua originated from somewhere near the star Vega. 2I/Borisov came from the direction of Cassiopeia, but 3I/Atlas. Its origin point doesn't align with any known star system within 50 light-years. It came from a void, a region of space where our telescopes see nothing but darkness and distant galaxies. Either it's been travelling for hundreds of thousands of years from a star we can't identify, or it changed direction at some point in its journey. Neither option makes sense without invoking something unusual. By late October 2024, as 3I/Atlas crosses the orbit of Jupiter, the scientific community is buzzing. Papers are being rushed through peer review. Observation time on major telescopes is being reallocated. Dr. Avi Loeb at Harvard, the same scientist who proposed that Oumuamua might be artificial, carefully avoids making bold claims this time out, but notes in a blog post the lack of outgassing despite the object's proximity to the Sun is reminiscent of what we saw with Oumuamua, but the surface reflectivity is completely different. We're dealing with something unprecedented. And he's right. By mid-November, 3I/Atlas is close enough to the Sun that any normal comet would be developing a visible tail. The solar radiation should be heating its surface, causing ices to sublimate and create that characteristic fuzzy coma. But nothing happens. The object remains pristine, sharp-edged in telescope images, reflecting sunlight like polished metal. NASA's Lucy mission team, which happens to have instruments pointed in the right direction, captures infrared data showing that 3I/Atlas's surface temperature is cooler than predicted, as if something is actively rejecting the Sun's heat rather than absorbing it. Then comes the rotation data, and this is where things get genuinely weird. Most asteroids tumble chaotically, rotating on multiple axes as they drift through space. Comets often develop non-gravitational accelerations from outgassing, which causes their rotation to speed up or slow down unpredictably. But 3I/Atlas rotates with mechanical precision. Every 8.7 hours, like clockwork, it completes one rotation. The deviation is less than 0.02 seconds over a 6-week observation period. Dr. Sarah Greenstreet from the University of Washington runs the numbers and publishes a note that sends ripples through the community. The rotational stability we're observing would require either an incredibly dense, perfectly balanced interior, or some form of active stabilization. Neither occurs naturally in objects this size. Active stabilization. The words hang in the air like a dare. No one wants to say what everyone's thinking, not yet. By December 2024, you're not the only one obsessed with this object. Amateur astronomers are tracking it. Podcasts are dissecting every new piece of data. And the object itself continues its steady plunge toward the inner solar system, completely indifferent to the speculation surrounding it. Its trajectory will bring it within 0.8 astronomical units of the Sun, roughly the distance of Venus, before slinging back out into the darkness from which it came. But before that happens, something else is brewing. The Sun, in its 11-year cycle of activity, is approaching solar maximum. Sunspots are appearing with increasing frequency. Coronal mass ejections are becoming more common, more violent, and one of them, building strength in a massive active region designated AR 3590, is about to put 3I/Atlas to a test that no interstellar object in recorded history has ever faced. You don't know it yet, but you're about to witness something that will make every anomaly you've observed so far look like a warm-up act. Because when the Sun decides to throw its full fury at this mysterious visitor, the universe is going to show you just how little we actually understand about what's possible. The Sun is not gentle. It never has been. For 4.6 billion years, it's been a roiling ball of nuclear fury, fusing 600 million tons of hydrogen into helium every single second. And while we like to think of it as our friendly neighbourhood star, the giver of life, the source of warmth, the reality is far more violent. The sun is a cosmic bully, constantly hurling tantrums into space in the form of solar wind, solar flares, and the truly terrifying phenomenon known as coronal mass ejections. Let me paint you a picture of what a CME actually is, because solar storm doesn't quite capture the apocalyptic scale we're talking about. Imagine 1 billion tons of superheated plasma. We're talking temperatures of several million degrees suddenly erupting from the sun's corona and blasting into space at speeds that make a bullet look stationary. We're talking 1 to 3 million miles per hour. This isn't some gentle cosmic breeze. This is a wall of electrified gas carrying the energy of millions of nuclear weapons, stretching across millions of miles of space, and it's heading somewhere with the inevitability of gravity itself. Now, Earth has experience with these cosmic punches. Our planet's magnetic field, that invisible shield generated by the churning iron in our core, deflects most of the solar wind and absorbs the shock of CMEs. You've seen the result, the northern lights. Wow. Those beautiful green and purple curtains dancing across polar skies, that's our planet bleeding off the energy from solar storms. Turning potential catastrophe into a light show. But even with our magnetic shield, powerful CMEs can wreak havoc. The Carrington event of 1859 remains the gold standard for solar fury. On September 1st of that year, British astronomer Richard Carrington was doing what astronomers do, sketching sunspots, when he witnessed something extraordinary, a solar flare so bright he could see it with the naked eye through his telescope's solar filter. Within hours, the fastest CME ever recorded slammed into Earth's magnetic field. Telegraph systems across Europe and North America went haywire. Operators reported receiving electric shocks. Telegraph paper spontaneously caught fire. The aurora borealis was visible as far south as the Caribbean, places where people had never seen such lights before and thought the world was ending. And that was in 1859, when our most advanced technology was the telegraph. Dr. Daniel Baker from the University of Colorado's Laboratory for Atmospheric and Space Physics ran the numbers on what a Carrington-level event would do to our modern civilization. His estimate, up to $2.6 trillion in damages. Power grids across entire continents would fail. Satellites would fry. GPS would go dark. Communication networks would collapse. We're talking about a potential technological apocalypse, Baker said in a 2014 interview. And the terrifying part is, it's not a matter of if, but when. More recently, we got a taste of what the sun can do. On March 13, 1989, a powerful CME triggered a geomagnetic storm that knocked out Hydro-Quebec's power grid, plunging 6 million Canadians into darkness for 9 hours. Transformers melted. The aurora was visible as far south as Texas, and that wasn't even close to Carrington levels. It was maybe 10% as powerful. But here's the thing about Earth: we're protected. We have that magnetic field. We have an atmosphere 300 miles thick that absorbs and dissipates energy. We have, quite literally, planetary scale armour. Objects in space. They have nothing. They're naked, exposed, vulnerable. When a comet encounters a CME, the results are spectacular and brutal. Take Comet Encke in 2007. As it swung through the inner solar system, a CME smashed into it head-on. NASA's stereo spacecraft captured the whole thing. You can watch the footage, it's available online, and what you see is horrifying. The comet's tail, which had been streaming behind it for millions of miles, simply vanishes, disconnected, ripped away by the magnetic forces in the CME like someone tearing a flag off a pole. The nucleus itself, the solid core of ice and rock, immediately starts shedding material at an accelerated rate as the storm's energy heats its surface to extreme temperatures. Or consider what happened to Comet Ison in 2013. as it approached the Sun, not even encountering a major CME. Just dealing with normal solar radiation, it simply disintegrated. One moment it was there, a pristine visitor from the Oort cloud making its first and only trip past our star. The next moment debris, a spreading cloud of dust and gas where a 4-billion-year-old object used to be. The Sun didn't need a storm to destroy it. Simple proximity was enough. This is what comets and asteroids face when they venture into the inner solar system, an environment of unrelenting hostility. Solar radiation bakes them, solar wind sandblasts them, and if they are unlucky enough to be in the wrong place when the Sun erupts, they get hammered by forces that make Earth's worst hurricanes look like a gentle breeze. Dr. Carey Lisser from Johns Hopkins Applied Physics Laboratory has spent decades studying what happens to small bodies in the solar system. In a 2019 paper, he described the process when a CME impacts a comet or asteroid. Several things happen simultaneously. The magnetic fields in the plasma induce powerful electric currents on the object's surface. The charged particles bombard and heat the exterior. Any volatile materials, water, ice, carbon dioxide, methane immediately begin sublimating. For objects without atmospheres or magnetic fields, there's no protection, no buffer. The energy transfer is direct and devastating. So now, picture this. It's early March 2025. 3I/Atlas is approximately 130 million miles from the Sun, closing in on its perihelion, the closest point in its trajectory, and on the Sun's surface, in active region AR 3590-something monstrous is building. You can see it in the magnetogram images from the Solar Dynamics Observatory. The magnetic field lines are twisting, braiding, storing energy like a coiled spring being compressed beyond its limits. Solar physicists at the Space Weather Prediction Center in Boulder, Colorado, are watching this region with growing concern. The sunspot group spans an area 15 times wider than Earth. The magnetic complexity is off the charts. Dr. Thomas Berger, in an internal memo later leaked to the press, writes, AR 3590 shows all the hallmarks of a region capable of producing an X-class flare and associated CME. Given the trajectory of 3I/Atlas, there's a non-trivial probability of a direct impact. On March 13th, at 1437 UTC, the Sun's surface erupts. And when I say erupts, I mean the kind of explosion that makes nuclear weapons look like firecrackers. A massive X8.2- class solar flare, the second most powerful classification we have, blasts electromagnetic radiation across the spectrum. But the flare is just the announcement. The real threat is what follows. A coronal mass ejection tears free from the Sun's corona, and this one is special. It's fast clocking in at 1.4 million miles per hour, making it one of the fastest CMEs recorded this solar cycle. It's massive, carrying an estimated 10 billion tons of plasma, and its trajectory, through the sheer cosmic coincidence that makes you wonder if the universe has a sense of drama, it's heading directly toward the exact spot where 3I/Atlas will be in approximately 26 hours. Astronomers around the world do the math and hold their breath, because for the first time in history, we're about to watch an interstellar object, something that survived the frigid darkness between stars for potentially millions of years, take a direct hit from our Sun's full fury. And based on everything we know about physics, about comets, about how matter behaves when exposed to that kind of energy, 3I/Atlas is about to be torn apart. At least, that's what should happen. But as you're about to see, should is a word the universe seems to enjoy proving wrong. March 14th, 2025, 1642 UTC. You're in the control room at the European Space Agency's Solar and Heliospheric Observatory SOHO facility outside Madrid. The room is packed, not just with the regular staff, but with scientists who flew in overnight, administrators clutching tablets, and a CNN crew that somehow got permission to document what everyone believes will be a historic moment, the destruction of an interstellar object in real time. The atmosphere is electric, tense. You can feel it in the way people keep checking their watches, in the nervous laughter that punctuates conversations, in the constant refreshing of data feeds on multiple screens. Because right now, the coronal mass ejection launched from the Sun 26 hours ago is about to slam into 3 I/8 at a relative velocity that makes car crashes look peaceful. Dr. Elena Vasquez from the University of Barcelona is coordinating observations from 7 different space telescopes. She's got Hubble pointed at the impact zone, James Webb standing by in infrared, the Solar Dynamics Observatory tracking the CME itself, Parker Solar Probe, which happens to be in a decent position, ready to measure particle densities. Even amateur astronomers with backyard telescopes are watching, hoping to catch something visible. This is our Shoemaker-Levy 9 moment, Vasquez says, referring to the comet that spectacularly crashed into Jupiter in 1994. Except this time, we're the observers, not the participants. The countdown is displayed on the main screen. 5 minutes, 4, 3. Someone brings coffee but nobody drinks it. The room gradually quiets. At 2 minutes, the only sound is the hum of cooling fans and the occasional beep from monitoring equipment. 1 minute, 30 seconds, and then impact. Except nothing happens, at least nothing you can see with the naked eye. But the instruments are screaming. Let me walk you through what they're recording because it's absolutely insane. The Parker Solar Probe, sitting about 40 million miles away, detects the shock wave first. Its fields instrument, designed to measure electromagnetic fields, registers a spike in magnetic field strength as the leading edge of the CME reaches 3 I/Atlas. We're talking about magnetic fields jumping from a few nanoteslas to over 150 nanoteslas in the span of seconds. To put that in perspective, that's roughly equivalent to the magnetic field strength you'd measure if you held a refrigerator magnet a few inches from the compass, except this is happening across millions of cubic miles of space. The plasma density goes ballistic. Normal solar wind at that distance from the Sun carries maybe 5 to 10 particles per cubic centimetre. When the CME hits, that number jumps to over 200 particles per cubic centimetre, the temperature of this plasma about 2 million degrees Celsius. For reference, the surface of the Sun is only 500 degrees. The stuff in a CME is heated by magnetic compression to temperatures that would vaporize any known material instantly. Dr. Justin Casper, who leads the Parker Solar Probe science team, later described what they saw. The energy density in that region of space temporarily exceeded anything we'd measured outside the solar corona itself. We're talking about roughly 10 to the 14th joules of energy being delivered to an object the size of 3 I/8 over the course of maybe 15 minutes. That's equivalent to detonating about 25,000 Hiroshima bombs directly on its surface. And 3 I/8. It just sits there. The Hubble Space Telescope captures images before, during, and after the impact. You'd expect to see the object brighten dramatically as its surface heats up and starts vaporizing. You'd expect to see a coma forming that fuzzy cloud of gas and dust that appears when comets get cooked. You'd expect to see the object's tail, if it had one, get stripped away like Comet Encke in 2007, but the before and after images are nearly identical. Same brightness, same sharp-edge profile. No visible outgassing, no debris cloud, nothing. Pull up the spectroscopy data, Vasquez says, and you can hear the confusion in her voice. The spectroscopic analysis should show emission lines, signatures of specific elements being heated and giving off light. When a comet gets hit by solar radiation, you see strong emission lines from water vapor, carbon monoxide, carbon dioxide, sodium, It's like a fingerprint of destruction, but 3I/Atlas's spectrum remains stubbornly unchanged. The same absorption lines it showed before the impact are still there. With no emission lines appearing, James Webb, operating in infrared, should be seeing something spectacular. Infrared detects heat, and an object getting bombarded with that much energy should light up like a Christmas tree in thermal imaging. But Webb's data shows only a modest temperature increase, from about -50 degrees Celsius to -35 degrees Celsius. That's it. 15 degrees of warming when it should have heated by hundreds of degrees, someone in the back of the room mutters. That's impossible. And they're right. It is impossible. Based on every physical model of how matter interacts with high-energy plasma, based on decades of observations of comets and asteroids, based on fundamental thermodynamics, this cannot be happening. Dr. Michael Kelly from the University of Maryland is on a video call from his office, analysing the data in real time. He runs the numbers 3 times before speaking. The albedo hasn't changed. The rotational period hasn't changed till 8.7 hours. Precise as a Swiss watch, the trajectory deflection is within measurement error, which means effectively 0. This object absorbed or deflected an amount of energy that should have at minimum altered its rotation, and possibly fragmented it entirely. Instead, it's fine. It's completely fine. Here's what makes this so deeply unsettling: energy doesn't just disappear. That's not how physics works. The first law of thermodynamics is pretty clear about this: energy is conserved. It transforms from one form to another, but it doesn't vanish into thin air. When that CME hit 3I/Atlas, all that kinetic energy, all that thermal energy, all that electromagnetic radiation, it had to go somewhere. It had to heat the object, or blast material off its surface, or transfer momentum and change its trajectory, or something. Energy in equals energy out, always, except apparently not this time. The CNN reporter is trying to get Vasquez to go on camera, asking for a comment, something to explain to viewers what they're witnessing. Vasquez just shakes her head, still staring at the screens. "I don't know what to tell them," she says quietly. "I don't know what we just saw." In the hours following the impact, as observatories continue monitoring 3I/Atlas, more anomalies emerge. The Solar Dynamics Observatory, which tracked the CME from the Sun all the way to the impact zone, notices something odd in the plasma flow patterns. Normally, when a CME encounters an obstacle, a planet, a comet, whatever you see disruption in the plasma, it flows around the object, creating a wake, like water around a rock in a stream. But in the SOHO images, enhanced and analysed by computer algorithms, the plasma flow around 3I/Atlas looks wrong. It's too smooth, too uniform. As if the object isn't just passively sitting there taking the hit, but somehow actively managing how the plasma interacts with it. Dr. Angelos Vourlidas from Johns Hopkins, one of the world's leading experts on CMEs, publishes a preliminary analysis that evening. His conclusion is cautious but disturbing. The observed interaction between the CME and 3I/Atlas is inconsistent with current models of plasma object dynamics. Either our models are fundamentally flawed, which seems unlikely given their success in predicting thousands of other interactions, or 3I/Atlas possesses properties not previously observed in natural celestial bodies. Properties not previously observed in natural celestial bodies. Read that phrase again. A scientist, being as careful as possible with language, is essentially saying this thing isn't behaving like a natural object. Social media explodes. #3IAtlas trends worldwide. The footage, such as it is, mostly just graphs and spectroscopic data, gets shared millions of times. Science communication channels on YouTube rush out explainer videos. And in the comment sections, in the Reddit threads, in the Twitter debates, the same questions keep appearing. What is this thing? Where did it really come from, and why is it so impossibly resilient back in the Soho control room? As the adrenaline fades and exhaustion sets in, you realise something profound. You just watched a mystery deepen instead of resolve. Every observation was supposed to give answers. Instead, you got more questions than ever, and the biggest question of all is one that nobody wants to say out loud yet. But everyone is thinking, what if 3I/Atlas survived that solar storm because it was designed to... Let's talk about what death looks like in space. Because before we can understand why 3I/Atlas's survival is so shocking, you need to see what normally happens when cosmic objects face the kind of violence we just witnessed. Picture yourself back on November 28th, 2013. Comet Ison, officially designated C2012 S1, is making its debut performance. This comet is special. It's a sun grazer, meaning its orbit will take it exceptionally close to the sun, skimming just 730,000 miles above the solar surface. For context, that's less than twice the distance from Earth to the Moon. Astronomers are excited because Ison is pristine. A virgin comet making its first journey from the Oort cloud, that distant shell of icy bodies surrounding our solar system. It's been frozen in deep space for 6 billion years, and now it's about to get the performance of a lifetime, except it doesn't survive the show. As Ison approaches perihelion, every solar telescope on and off Earth is watching. The comet is beautiful. Its tail stretches for millions of miles. Its coma glows brilliantly as solar radiation vaporizes ice from its nucleus. And then, as it rounds the sun, it simply disintegrates. The nucleus, estimated at about 1.2 miles across, breaks apart under thermal and tidal stress. Within hours, all that remains is a diffuse cloud of dust. 4 billion years of existence, ended in an afternoon. Dr. Carey Lisser, who we heard from earlier, put it bluntly, Ison went into the sun's neighbourhood as a comet and came out as debris field. The thermal shock and tidal forces were more than its structure could handle. And here's the thing, Ison didn't even face a CME. It just got too close to normal solar radiation. Or consider Comet Shoemaker-Levy 9, though technically that's a different kind of catastrophe. In July 1994, this comet already broken into 21 fragments by Jupiter's tidal forces during a previous close pass slammed into Jupiter's atmosphere over the course of 6 days. The Hubble Space Telescope watched as each fragment hit, creating fireballs larger than Earth itself. The energy released by the largest impact, Fragment G, was estimated at 6 million megatons of TNT, 600 times the entire world's nuclear arsenal. The dark scars in Jupiter's atmosphere were visible for months. What does this tell us? It tells us that comets are fragile. They're not solid rocks. They're dirty snowballs. As astronomer Fred Whipple famously described them, loose aggregations of ice, dust, and rock held together by weak gravity and frozen volatiles. When you heat them, they fall apart. When you hit them with tidal forces, they crumble. When you subject them to the kind of energy that a CME carries, they should vaporize. Let's look at asteroids, which are tougher. These are rocky or metallic bodies, much more robust than icy comets. But even they have limits. On February 15th, 2013, a 66-foot asteroid entered Earth's atmosphere over Chelyabinsk. Russia. The energy released as it exploded in the air was equivalent to about 500 kilotons of TNT, roughly 30 times the Hiroshima bomb. The shockwave damaged thousands of buildings and injured over 1,500 people, mostly from broken glass. And that was just atmospheric entry, not even a direct impact. The stresses from rapid heating and deceleration tore the asteroid apart at an altitude of 18 miles. Now think about what a CME does. Dr. Tamitha Skov, a space weather physicist who's become famous for her accessible explanations of solar phenomena, breaks it down. A coronal mass ejection isn't just heat, it's a triple threat. First, You got the thermal component plasma at millions of degrees hitting the object's surface. Second, you've got kinetic impact, billions of tons of matter moving at over 1,000,000 miles per hour, transferring momentum. Third, you've got the electromagnetic component, intense magnetic fields that induce electric currents, which generate their own heat and can literally rip charged particles off the surface. Any one of these components alone can damage a small body. All three together, it's like hitting something with a blowtorch, a sandblaster, and a lightning bolt simultaneously. The famous case that every planetary scientist references is Comet Encke's tail disconnection event in April 2007. This wasn't even a particularly powerful CME, maybe mid-level, on the scale of solar storms. But when it hit Comet Encke, the results were dramatic and immediate. The stereo spacecraft captured the moment when the magnetic fields in the CME literally severed the comet's tail. One moment there was a beautiful ion tail streaming behind the nucleus for millions of miles. The next moment gone, disconnected, floating away like a ghost. The nucleus itself began showing signs of enhanced outgassing, its surface temperature spiking as the CME's energy pumped heat into the icy material. Dr. Geraint Jones from University College London, who analysed the Encke event extensively, published findings that should have been the playbook for understanding the 3/Atlas impact. The interaction between the CME and Encke's magnetosphere, such as it is for a comet, resulted in rapid energy transfer. Surface ice sublimation rates increased by a factor of 5 to 7. The ion tail disconnection was caused by magnetic reconnection events, where the comet's local magnetic field, induced by ionized gases around it, couldn't withstand the magnetic pressure from the CME. The physics here is well understood and predictable. Predictable? That's the key word. Because when you study enough of these interactions, comets being heated by solar radiation, asteroids being sandblasted by solar wind, objects encountering CMEs, you develop models, mathematical models that predict exactly what should happen based on the object's size, composition, distance from the sun, and the energy involved. These models work. They've been tested against thousands of observations. They've successfully predicted the behaviour of comets like Hale-Bopp, asteroids like Bennu, and countless smaller bodies. These models all said the same thing about what should happen to 3/Atlas catastrophic damage. Let's run the numbers specifically. 3/Atlas is approximately 400 meters in diameter. The CME that hit it delivered roughly 10 to the 14th joules of energy over 15 minutes, as Parker's solar probe measured. Now, if we assume 3/Atlas has a composition similar to typical comets, about 60% water ice, 30% rocky material, 10% other volatiles like carbon dioxide and methane, we can calculate how much material should have vaporized. Water ice has a specific heat capacity of about 2000 joules per kilogram per degree Celsius, and a heat of sublimation of about 8 million joules per kilogram. If even just 1% of the CME's energy was absorbed by the surface, which is an extremely conservative estimate, that would be 10 to the 12th joules, enough to sublimate roughly 360,000 kilograms of ice. That's 360 tons for an object 400 meters across. Losing 360 tons of surface material would create a clearly visible coma and would definitely show up in spectroscopic data as emission lines from water vapor. But we saw nothing. 0 emission lines, no coma, no mass loss. Maybe it's not a comet, you might say. Maybe it's a solid rocky asteroid or even metallic. Okay, let's go with that. Rocky asteroids have a specific heat capacity of about 800 joules per kilogram per degree Celsius. Even if 3/Atlas is solid rock, absorbing 10 to the 12th joules should have raised its surface temperature by hundreds of degrees. We should have seen that in James Webb's infrared data. Instead, 15 degrees of warming. 15. Or maybe it's metallic, like an iron asteroid. Iron's specific heat capacity is about 450 joules per kilogram per degree Celsius, and its melting point is 538 degrees Celsius. But even a pure iron object would have shown significant heating, and besides, the spectroscopic data from before the impact showed silicate absorption features, not metallic signatures. It's not made of iron. Dr. Alan Harris from the Space Science Institute ran these calculations and published them in a hastily written paper titled Energy Budget Discrepancies in the 3I/Atlas EME Interaction. His conclusion is as dry as scientific language gets, but the implications are staggering. No plausible composition or structural configuration for 3I/Atlas, using known materials and properties, can account for the observed thermal response to the measured energy input. The object appears to be violating basic thermodynamic principles, which suggests either a fundamental flaw in our measurements, which seems unlikely given the redundancy of observations or properties that are not consistent with naturally formed celestial bodies. Translation: this shouldn't be possible with anything nature makes. Here's another angle trajectory deflection. When a CME hits an object, it transfers momentum. It's basic physics. Force equals mass times acceleration, and momentum is conserved. Even if 3I/Atlas somehow magically didn't heat up, it should have been pushed, however slightly. The Parker Solar Probe measured the CME's momentum flux. Multiple observatories tracked 3I/Atlas's position before and after impact with subarc-second precision. The expected trajectory deflection, even in the most conservative models, should have been at least 15 arcseconds easily measurable. The actual deflection less than 2 arcseconds, which is within measurement error, effectively zero. It's as if the object has mass way beyond what its size suggests, making it too massive to budge. Or as if it's somehow anchored. Though anchored to what? Or, and this is the explanation nobody wants to voice yet, as if something actively compensated for the momentum transfer, maintaining the original trajectory through deliberate correction. When you put all these pieces together, the lack of thermal response, the absence of outgassing, the trajectory stability, the unchanged spectral signature, you're forced to confront an uncomfortable reality. 3I/Atlas didn't just survive the CME impact, it ignored it, and natural objects, formed by random cosmic processes, don't ignore physics. They can't, unless they were built to... So what could possibly explain this? Let's walk through the possibilities, because scientists don't just jump to aliens at the first sign of weirdness. There's a process here, a hierarchy of explanations that starts with the mundane and only ventures into the extraordinary when everything else fails. And trust me, in the weeks following the CME impact, every research group on the planet was trying to find a conventional explanation that could make the data make sense. Hypothesis 1. It's all ice. Exotic ice. Doctor. Robert Pappalardo from NASA's Jet Propulsion Laboratory was one of the first to suggest this. What if 3I/Atlas is composed primarily of a type of ice we haven't encountered in large quantities before, specifically amorphous ice or high-pressurized polymorphs that are extremely stable and have thermal properties very different from normal crystalline ice? Here's the logic. Normal ice, the kind in your freezer, has a crystalline structure. Water molecules arrange themselves in hexagonal patterns. But when you form ice under different conditions, extreme cold, extreme pressure, rapid cooling, you can get amorphous ice, where the molecules are arranged randomly, more like glass. Some forms of high-pressure ice, discovered in laboratory settings, can remain stable at relatively high temperatures. Amorphous ice has some interesting properties. It's denser than regular ice. It can absorb and store more energy before transforming. If 3I/Atlas's surface were coated in a thick layer of amorphous ice, maybe that could explain the thermal resilience. The energy from the CME would go into transforming the amorphous structure into crystalline ice rather than vaporizing it, a process that absorbs heat without creating visible outgassing. Sounds plausible. Right, except there are problems. Big ones. First, spectroscopic observations don't show the absorption features you'd expect from amorphous ice. Dr. Sylvia Protopapa from the Southwest Research Institute checked the data exhaustively. The spectral signature we're seeing has sharp absorption features consistent with crystalline water ice and silicates. Amorphous ice shows broader, more diffuse features. We're not seeing that. Second, even if the surface were amorphous ice, the sheer amount of energy delivered by the CME should have exceeded the heat capacity of any reasonable thickness. You'd need a layer of amorphous ice kilometers thick to absorb that much energy without showing any effects. But 3I/Atlas is only 400 meters across. The math doesn't work. Third, and perhaps most damning, amorphous ice doesn't explain the trajectory stability or the rotational precision. It's a dead end. Hypothesis. 2. Dense metallic core. Maybe 3I/Atlas is what we call a differentiated body, one that formed with enough internal heat to separate into layers, with heavy metals sinking to the core and lighter materials forming a crust. Our own Earth is differentiated, so is Mercury. If 3I/Atlas has an unusually dense metallic core, maybe 80% or 90% of its total mass, that could explain why the CME didn't budge. High mass means high inertia means hard to push. The dense core could also explain the thermal stability. Metals conduct heat very efficiently. A large metallic core could act like a heat sink, absorbing the energy from the surface and distributing it throughout the interior before the surface temperature rises significantly. It's like how a cast iron pan heats slowly because it's soaking up and spreading out the thermal energy. Dr. Eric Asfau from the University of Arizona, an expert in planetary formation, initially liked this hypothesis. A metallic core comprising 85 to 90% of the object's mass would give you the thermal mass and inertial stability we're observing. We know from meteorite studies that some asteroids are almost entirely metal. These are the cores of shattered protoplanets, stripped of their rocky mantles by ancient collisions. But again, the data doesn't cooperate. The spectroscopic signature shows silicates and ice, not metal. If 3I/Atlas has a huge metallic core, it's hidden under a crust that shows no metallic features whatsoever. And here's the kicker: the object's overall density, calculated from its gravitational influence on its trajectory and the way it interacts with solar radiation pressure, comes out to about 2.3 grams per cubic centimetre. That's roughly the density of ordinary rock. Iron has a density of 7.9 grams per cubic centimetre. If 90% of 3I/Atlas's mass were iron, the overall density should be much higher. The numbers don't add up. Hypothesis 3. It's a rubble pile with unusual structure. Many asteroids aren't solid objects. They're rubble piles, loose collections of smaller rocks held together by weak gravity, with lots of empty space between the pieces. Asteroid Bennu, which NASA's OSIRIS-REx mission studied up close, is like this, about 50% empty space. When you hit a rubble pile with energy, it can absorb the impact by compressing slightly, like a sponge. The individual rocks can shift and dissipate energy without the whole structure flying apart. Dr. Patrick Michel from the Côte d'Azur Observatory suggested this in a March paper. If 3I/Atlas has an extremely high porosity, perhaps 70% or more, combined with a specific arrangement of internal voids, It might be able to absorb the CME's energy through mechanical compression and internal friction rather than through thermal processes we can observe externally. It's creative thinking, but it still doesn't explain everything. High porosity objects should show it in their spectra you get different light scattering properties. They should also show it in their thermal behaviour over time. As 3I/Atlas approached the Sun over months, a highly porous object would heat and cool in distinctive ways due to the trapped spaces affecting heat flow. We're not seeing those signatures. Plus, rubble piles are mechanically weak. They're held together by gravity, which for a 400-metre object is incredibly feeble. The rotational precision we're observing 8.7 hours, varying by less than 0.02 seconds over weeks, is inconsistent with a loose aggregate. Rubble piles tend to have chaotic, evolving rotations because the components shift. This thing rotates like a solid, perfectly balanced flywheel. Hypothesis 4. Surface coating or crust. What if 3I/Atlas has some kind of unusual crust or coating that acts as a thermal shield? Some asteroids develop what's called a thermal lag surface, a layer of dust or degraded material that insulates the interior. But this is usually thin, millimeters to centimeters, and it delays heating rather than preventing it. Dr. Yanga Fernandez from the University of Central Florida proposed a more exotic version. What if exposure to interstellar radiation over millions of years created a surface layer of radiation-processed material, heavily cross-linked organic compounds, similar to tholins but more extreme? Such a layer could have very unusual thermal properties. Tholins are complex organic molecules created when simpler compounds are exposed to UV radiation or charged particles. They're reddish-brown, sticky, and have been found on Pluto, Titan, and various outer solar system objects. A layer of heavily radiation-processed tholins might indeed have interesting thermal properties. But once again, spectroscopy says no. We're not seeing the strong organic absorption features that tholins produce. And even the most optimistic estimates for how thick such a layer could grow, maybe a metre or two over millions of years, wouldn't be enough to shield against the CME's energy penetration. Hypothesis 5. It's rotating and radiating efficiently. Maybe the 8.7-hour rotation is key. As 3I/Atlas spins, different parts of its surface face the incoming CME energy. If the object has very high thermal conductivity and efficient radiation properties, it might spread the heat around quickly and radiate it away before any single spot gets hot enough to show dramatic effects. The problem, the CME impact lasted about 15 minutes. That's nowhere near enough time for rotation to significantly distribute heat across the surface. And infrared observations from James Webb show that the whole object heated fairly uniformly, not in a pattern you'd expect from rotating through a beam of energy. This hypothesis is dead on arrival. So where does that leave us 5 conventional explanations? All of them reasonable starting points, and all of them failing to match the observations. Dr. Michelle Bannister, who we heard from earlier, summed up the frustration in a leaked email that made the rounds. We're running out of natural explanations. Every hypothesis requires special pleading unusual composition that doesn't match spectra, impossible densities, structures that violate mechanical principles. At some point, you have to consider that maybe we're looking at this wrong. Maybe 3I/Atlas isn't trying to be a comet or an asteroid. Maybe it's something else entirely. Something else entirely. Those words hung in the air of countless research meetings, Zoom calls, and late-night lab sessions. Because once you exhaust the conventional explanations, you're left staring at the unconventional ones. And in this case, the unconventional explanation has a name that makes serious scientists very uncomfortable. Active shielding. The term appeared first in an internal NASA memo. then in a speculative paper posted to our arXiv, the preprint server, where scientists share work before peer review. The argument goes like this. What if 3I/8LACE has some kind of protective system that actively manages energy input, not passive thermal properties, but an active response mechanism, something that detects incoming radiation or particles and generates a counteracting effect, a magnetic field bubble, a plasma deflection system, some kind of energy dissipation technology we don't understand? The moment that paper hit arXiv, the scientific community split into camps. One group dismissed it as premature speculation verging on pseudoscience. Dr. Phil Plait, the astronomer and science communicator, wrote in his blog, "Let's not jump to Star Trek explanations when we haven't exhausted normal physics yet. Extraordinary claims require extraordinary evidence. And right now we have extraordinary observations, not extraordinary evidence." But another group, quieter, more cautious, started to seriously consider it. Not because they wanted to believe in alien artifacts, most scientists find that idea professionally uncomfortable at best, but because the data was forcing their hand. When every natural explanation fails, what's left, Doctor? Avi Loeb, who'd been carefully quiet since the Oumuamua days, finally weighed in during a Harvard seminar in late March. "I'm not saying 3I/Atlas is artificial. I'm saying we should consider all hypotheses that fit the data, including ones that make us uncomfortable. Science isn't about what we wish to be true. It's about what the evidence suggests. And right now, the evidence suggests something we don't understand. The question hanging over everything. The question that turned 3I/Atlas from an astronomical curiosity into a global obsession. If this thing has shielding technology, who built it, and why is it here? Here's the thing about 3I/8LACE that nobody talks about enough. This wasn't its first impossible moment. The solar storm survival was just the headline grabber, the dramatic climax that made CNN. But if you'd been paying attention, and a handful of astronomers definitely were, you'd have noticed that this object had been breaking the rules since day one. The pattern was there. We just weren't ready to see it. Let's rewind to October 2024, about 6 weeks after discovery. 3I/Atlas is crossing the orbit of Jupiter, and astronomers are still in the data-gathering phase. You're collecting photometry measuring how bright the object appears over time. For tumbling asteroids, brightness varies in predictable ways as different surfaces rotate in and out of view. Dark side faces you dimmer. Bright side faces you brighter. Simple geometry, except 3I/Atlas's light curve, the graph of brightness over time is weird. Dr. Hannah Sizemore from the Planetary Science Institute was one of the first to notice the amplitude of brightness variation is extremely small, less than 0.05 magnitudes. That suggests either a nearly spherical object, which is unusual for something this size. Small bodies are typically irregular, or a surface with remarkably uniform reflectivity. Both options are strange, but it gets stranger. When you analyse the light curve with Fourier transforms mathematical tools that break down complex patterns into simpler components, you find that the rotation is not just stable, it's too stable. Natural tumbling bodies show subtle variations in their rotation periods over time, due to what's called Yop effect, a torque created by uneven heating from sunlight that gradually speeds up or slows down rotation. It's weak, but measurable over weeks or months. 3I/Atlas shows no Yop effect, 0. The rotation period of 8.7 hours doesn't change by even 1/100th of a second over 2 months of observations. Dr. Stephen Lowry from the University of Kent, who literally wrote the textbook on Yop effects, published a note. Either 3I/Atlas has a perfectly symmetrical shape and perfectly uniform surface properties, which natural formation processes don't produce, or something is actively stabilizing its rotation against external torques. There's that word again, active. Actively stabilizing, then there's the brightness anomaly from November. On November 18th to 2024 3I/Atlas suddenly brightened by 0.3 magnitudes over the course of about 6 hours, then returned to its baseline brightness over the next 8 hours. This kind of brief brightening happens with comets. It's called an outburst, caused by a sudden release of gas from beneath the surface. Fresh ice gets exposed, vaporizes rapidly, carries dust with it, and boom, temporary brightening. But spectroscopic observations during 3I/Atlas's brightening event showed no emission lines, no water vapor, no carbon monoxide, no dust. The brightening happened without any detectable mass loss. Dr. Colin Snodgrass from the University of Edinburgh, who specialises in cometary outbursts, was baffled. We've observed hundreds of cometary outbursts. They always produce gas and dust that we can detect spectroscopically. This brightened without outgassing. That's not how comets work. So what caused it? Some speculated internal structural changes, maybe ice transforming from one phase to another, releasing stored energy as light somehow. Others suggested impact by a micrometeorite. But these explanations felt forced, retrofitted to explain an observation that didn't fit any existing model. The December trajectory anomaly was even more provocative. As 3I/Atlas approached the inner solar system, multiple observatories were tracking its position with extreme precision. You need this data to refine the orbit, to predict exactly where the object will be months from now. Normally, once you have enough observations, the orbit calculation converges, the uncertainties shrink, and you get a reliable prediction. But with 3I/Atlas, something odd kept happening. The object's position would deviate slightly from the predicted trajectory, not by much, maybe 50 to 100 kilometers, which sounds like a lot, but in astronomical terms is tiny. Then, over the next few days, it would drift back toward the predicted path. It was as if the object was wandering off course, then correcting itself. Dr. David Farnokia from NASA's Center for Near-Earth Object Studies handles orbit calculations for thousands of asteroids and comets. He's seen every kind of orbital weirdness. In a January 2025 teleconference, he said something that made a lot of people uncomfortable. These position residuals, the differences between where we observe 3I/Atlas and where we predict it, should we show a pattern that's consistent with small delta V maneuvers, very small, maybe a few centimeters per second velocity change, applied periodically. Comets can do this through outgassing, creating non-gravitational accelerations, but 3I/Atlas isn't outgassing. Delta V maneuvers, that's the term we use for spacecraft changing their trajectory with thrusters. He was describing the object's motion using spacecraft terminology because the pattern looked like spacecraft behavior. When pressed on this, Farnokia backtracked slightly. I'm not saying it's maneuvering. I'm saying the orbital residuals have characteristics similar to what we'd see from small thrust events. There could be natural explanations we haven't considered, but it's worth noting indeed, social media went wild with that one. #3I/Atlas maneuvers trended. The UFO community declared victory. Serious scientists tried to distance themselves from the speculation. But the data was the data. Position residuals that looked like course corrections, brightness changes without outgassing, rotational stability that defied natural processes. And then there was the radio anomaly. This one didn't get much press because it was buried in technical papers. But it's perhaps the strangest detail of all. In late January 2025, the Arecibo successor facility, the massive new radio telescope in Puerto Rico that replaced the collapsed original, pointed at 3I/Atlas as part of a radar survey. Radar astronomy is powerful. You bounce radio waves off an object and analyze the return signal to learn about surface texture, rotation, size, and sometimes even internal structure. The radar observations of 3I/Atlas were unusual. Dr. Anne Verkey, who led the observations, described it in a paper submitted to Icarus Journal. The radar cross-section is significantly higher than predicted based on the object's optical size. The return signal shows anomalous polarization characteristics. And we detected a faint narrowband emission at 1420 MHz that persisted for approximately 40 minutes. Let me break that down. High radar cross-section means the object reflects radio waves more efficiently than expected, possibly indicating a metallic or unusually smooth surface. Anomalous polarization suggests the surface isn't rough rock, but something more organized or structured. And that narrowband emission at 1420 MHz. That's the hydrogen line. One of the most important frequencies in radio astronomy. It's the frequency at which neutral hydrogen naturally emits radio waves. And it's so important that international agreements protect it from interference. It's also a frequency that SETI, the search for extraterrestrial intelligence, pays particular attention to, because any technological civilization would know about it. It's considered a logical frequency for interstellar communication. Now, before you get too excited, narrowband emissions can have natural causes. Ionized hydrogen in a comet's coma can emit at this frequency. But 3I/Atlas doesn't have a detectable coma. The emission was coming from the object itself or very close to it, and it lasted exactly 40 minutes before stopping, which is oddly specific for a natural phenomenon. Verkey was extremely careful in her paper. We cannot rule out instrumental artifacts or transient environmental effects. However, the emission's characteristics warrant follow-up observations. That scientists speak for. This is weird and I don't know what to make of it. The paper included a data plot showing the emission spike. Amateur radio enthusiasts got their hands on it and started analysing the signal characteristics. Some claimed to find patterns, regular pulses, even what they swore was modulation. But radio signals are notoriously easy to overinterpret. You can find patterns in noise if you look hard enough. The human brain is wired to seek patterns, even where none exist. Professional SETI researchers were more cautious. Dr. Jill Tarter, who spent decades searching for alien signals, offered perspective. A single, brief detection at a common natural frequency proves nothing. We need repeatability, additional frequencies, something that screams artificial beyond a reasonable doubt. This is interesting, but it's not a smoking gun. Still, the Breakthrough Listen project funded by billionaire Yuri Milner to search for techno-signatures added 3I/Atlas to their target list. In February, they pointed the Green Bank telescope at it for 10 hours straight, scanning across a wide range of frequencies. They detected nothing. No repeat of the 1420 MHz emission. No other unusual signals. Just the normal thermal radiation you'd expect from a cold object in space. Does that mean the Arecibo detection was a fluke, maybe? Or maybe whatever produced that emission only operates occasionally. Or maybe it responded to being actively probed by radar, and then went quiet when passive listening began. You can construct narratives to fit any pattern. By March 2025, before the solar storm hit, a small but growing group of astronomers had compiled what they called the anomaly list for 3I/Atlas. Hyperbolic trajectory from an empty region of space unusually high and uniform albedo rotational stability beyond natural Yorp effects. Brightness variation without outgassing, position residuals consistent with trajectory corrections, high radar cross-section with anomalous polarization, transient narrowband radio emission, spectral signatures that don't match any known composition completely. 8 anomalies, individually, each could potentially be explained away with enough creative thinking, but together they painted a picture of an object that didn't behave like any natural asteroid, comet, or interstellar wanderer we'd ever seen. Dr. Sarah Seeger from MIT, who spent her career studying exoplanets and thinking about biosignatures, made an important point during a symposium in planetary science. We're taught to look for patterns. One unusual data point is an outlier. 2 might be a coincidence. 3 starts to look like a signal. When you get to 8 independent anomalies, you're not looking at noise anymore. You're looking at something that demands explanation. And then the solar storm hit, and anomaly number 9, complete immunity to a direct CME impact, got added to the list. Suddenly, 3I/Atlas wasn't just an academic curiosity. It was front-page news. It was the lead story on cable news. It was trending worldwide. Because now even skeptics had to admit something about this object was profoundly wrong, or profoundly right, depending on your perspective. The pattern wasn't just emerging anymore. It was screaming, and the question everyone was asking, from professional astronomers to random people on Twitter, what exactly are we dealing with here? So let's address the elephant in the room. The question that's been hanging over this entire story like a storm cloud. The possibility that makes some scientists uncomfortable and others quietly excited. Could 3I/Atlas be artificial? Could this interstellar visitor be a probe, a spacecraft, or some kind of manufactured object sent by an extraterrestrial civilization? Before you dismiss this as science fiction, let me remind you we've done exactly this ourselves. Right now, as you listen to this, 5 human-made objects are on interstellar trajectories. Voyager 1 and Voyager 2, launched in 1977, have both left the solar system and are coasting through interstellar space. Pioneer 10 and 11 are out there too, though we've lost contact with them. And New Horizons, after its spectacular Pluto flyby, is also headed for the stars. These spacecraft will drift through the galaxy for millions, possibly billions of years. Eventually, some of them might enter another star system. Now imagine you're an astronomer in that distant star system. Thousands of years from now, you detect Voyager 1 passing through. What would you see? A small object, maybe 10 meters across, including the extended antenna, moving on a hyperbolic trajectory, not outgassing like a comet, rotation rate stable because it was designed for attitude control, made of aluminum and titanium alloys, materials you might not expect in a natural object, emitting faint radio signals from its decaying power source. Would you recognize it as artificial? Maybe. Would you be certain? That's harder to say. Dr. Avi Loeb, who we've heard from before, has made a career lately of pushing the conversation about technological signatures in space. In his 2021 book Extraterrestrial, he argued that Oumuamua's unusual properties, extreme elongation, non-gravitational acceleration, high reflectivity could be explained if it were a light sail, a thin sheet of material pushed by radiation pressure. The astronomy community largely rejected this hypothesis, preferring natural explanations even if they required some creative assumptions. But with 3I/Atlas, even skeptics are finding it harder to dismiss the artificial hypothesis outright. In a March 2025 interview with Scientific American, Loeb said, "I'm not claiming 3I/Atlas is a spacecraft. I'm saying we should examine that possibility with the same rigor we apply to natural explanations. Right now, we have an object that violates our expectations in multiple independent ways. If this were a single anomaly, fine. but we're looking at a constellation of unusual properties. At what point does intellectual honesty require us to consider all possibilities? So let's do that. Let's seriously consider what 3I/Atlas would look like if it were artificial, and whether that hypothesis actually fits the data better than natural explanations. First, the shielding. If 3I/Atlas is a manufactured object designed for interstellar travel, having some kind of protective system makes perfect sense. Interstellar space is harsh. You've got cosmic rays, high-energy particles that can damage materials over time. You've got micrometeoroids, tiny grains of dust that hit with tremendous energy at interstellar velocities. And if you're entering a star system, you'll encounter increased radiation, solar wind, and potentially coronal mass ejections. An advanced civilization building an interstellar probe would anticipate these hazards. They'd engineer protection, maybe a magnetic shield that deflects charged particles. We've theorized about this for human Mars missions. Maybe a surface coating of exotic materials with high thermal tolerance. Maybe even active cooling systems, radiators that dump excess heat efficiently. The solar storm immunity suddenly makes sense in this framework. It's not that 3I/Atlas violated physics, it's that it was designed to handle exactly this kind of energy input. The CME wasn't an unexpected catastrophe, it was an anticipated obstacle that the object's systems were built to manage. Second, the trajectory control. Those position residuals that looked like small delta V maneuvers. If 3I/Atlas is artificial, they are small delta V maneuvers. Maybe it's performing course corrections to target a specific destination in the solar system. Maybe it's adjusting to optimize its scientific observations, changing its path slightly to get better viewing angles of planets or phenomena of interest. Dr. Les Johnson, a NASA engineer who works on advanced propulsion concepts, offered a thought experiment. If I were designing an interstellar probe, I'd give it some propulsion capability for trajectory refinement. Nothing massive, you don't need huge delta V when you're already moving at interstellar velocities. Just enough for small adjustments. Ion drives, perhaps, or some even more efficient technology we haven't invented yet. The thrust would be minimal, nearly undetectable unless you were looking very carefully. Which is exactly what we see. Trajectory changes so small that they're at the edge of detectability, consistent with low-thrust propulsion. Third, the rotational stability. Natural tumbling is chaotic. But if you're an interstellar probe with instruments, you want stable pointing, you want your sensors aimed at your targets, your communication antenna pointed toward home. Your solar panels, if you have them optimally oriented, you'd have reaction wheels or some attitude control system maintaining precise rotation. That 8.7-hour period, stable to 0.02 seconds, that's what controlled rotation looks like. That's what spacecraft do. Fourth, the radio emission at 1420 MHz. If you're an interstellar probe and you want to signal I'm artificial to anyone listening, you might transmit at the hydrogen line frequency. It's a universal constant. Any civilization capable of radio astronomy knows about it. It's like leaving a calling card. The fact that the emission was brief and hasn't repeated might mean the probe was doing a one-time announcement. I'm here, I'm not a rock, pay attention. Or maybe I'm reading too much into what could be natural hydrogen emission from some process we don't understand. This is the danger of pattern seeking. You can construct narratives that sound compelling but aren't necessarily true. Fifth, the composition mystery. If 3I/Atlas is manufactured, it might be made of materials we don't have reference samples for. Alloys or composites or metamaterials engineered for specific properties. The spectroscopic signatures we're detecting silicates, ice signatures, Traces of metals might be surface contamination picked up during millions of years travelling through interstellar space, obscuring the actual hull material underneath. It's like finding an old shipwreck encrusted with barnacles and corals. The biology on the surface doesn't tell you what the ship itself was made of. Put it all together, and the artificial hypothesis provides a framework that explains every anomaly. Hyperbolic trajectory. It's going somewhere, or came from somewhere specific. High albedo, reflective hull material, rotational stability, attitude control system, no outgassing during brightening internal systems activating, not ice vaporizing, trajectory corrections, active navigation, solar storm immunity, engineered shielding, radio, emission, deliberate signal or systems activity, anomalous radar return, manufactured surface structure. It's elegant, maybe too elegant, because here's the problem with the artificial hypothesis: it raises far more questions than it answers. If 3I/Atlas is a probe, who built it? Where did it come from? That empty region of space its trajectory points back to, is that where its builders are? Or is that just where it was when it changed course? How long has it been travelling at 34 kilometers per second? Covering interstellar distances takes a long time. Even to the nearest star system, 4.2 light-years away, you'd need over 37,000 years at that speed. Is it still functional? Or is it a derelict if functional? What's it doing here? Observing, collecting data, searching for something? Is it autonomous? Or is someone controlling it from light-years away? Receiving data on decades-long time delays. And here's the really unsettling question: is it alone if one civilization sent one probe? Might there be others? Might our solar system be full of these things, silently observing? And 3I/Atlas is just the first we've noticed because it happened to pass close enough. Dr. Jason Wright from Penn State University, who studies technosignatures, cautioned against jumping to conclusions in a blog post. The artificial hypothesis is seductive because it's exciting, but excitement isn't evidence. We need to be extraordinarily careful here. The history of astronomy is littered with anomalies that turned out to have mundane explanations once we understood the underlying physics better. Pulsars were once jokingly called LGM signals little green men until we realized they were rotating neutron stars. Fast radio bursts seemed inexplicable until we found natural mechanisms that could produce them. He's right to be cautious. Science progresses through skepticism, through demanding evidence, through exhausting natural explanations before invoking extraordinary ones. Carl Sagan's famous maxim applies: extraordinary claims require extraordinary evidence. But here's the counterpoint, articulated by Dr. Ravi Kopparapu from NASA's Goddard Space Flight Center. Skepticism is essential, but it can't become denial. If we refuse to seriously investigate the artificial hypothesis because it makes us uncomfortable or seems too sensational, we're not being good scientists, we're being ideologues. The data suggests something unusual. We have a responsibility to follow the data wherever it leads, even if it leads somewhere we didn't expect. So where does that leave us? With a mystery that refuses to resolve cleanly into either category. 3I/Atlas is too weird to be a normal comet or asteroid, but we don't have definitive proof it's artificial either. We're stuck in epistemic limbo, with compelling evidence pointing in both directions, no smoking gun to settle the question. What we need is more data, direct observation, high-resolution imaging, spectroscopy across wider wavelength ranges, radar mapping to see surface structure, maybe even a flyby mission, a spacecraft sent to intercept 3I/Atlas and study it up close. Dr. Kelly Fast from NASA's Planetary Defense Coordination Office confirmed in a press conference that discussions were underway. We're exploring the feasibility of a rapid response mission to 3I/Atlas. given its trajectory and speed, we have a narrow window, probably weeks, maybe a couple of months, to launch something that could catch it before it leaves the inner solar system. It would be challenging, probably requiring a gravity assist and some very clever orbital mechanics, but it might be possible. Might be possible. That's where we are. Scrambling to answer questions we never expected to ask. Staring at an object that defies easy categorization. Wondering if we're witnessing the most important astronomical discovery in human history, or just seeing patterns in noise because we want to believe there's something more out there. And while scientists debate and plan and argue, 3I/Atlas continues its journey through our solar system, indifferent to our speculation, keeping its secrets. Retry F. Let's talk about what the scientists are actually saying, not the headlines, not the Twitter speculation, not the YouTube videos with dramatic thumbnails, the real conversations happening in research institutions, university departments, and government agencies. Because there's a fascinating split happening in the scientific community, and it's revealing just how unprecedented this situation really is. You have to understand astronomers are trained to be conservative. Careers are built on careful analysis, peer review, reproducible results. You don't make bold claims without bulletproof evidence. You definitely don't invoke aliens unless you've exhausted literally every other possibility. The professional incentives all push toward caution, so when Dr. Paul Byrne, a planetary scientist at Washington University, tweeted in late March, "I've spent 15 years studying planetary surfaces. I've never been so uncertain about what I'm looking at. Every time I think I have an explanation for 3I/Atlas, the data contradicts me. This is both frustrating and exhilarating." That meant something. That was a well-respected scientist admitting genuine uncertainty in public, which almost never happens. Behind closed doors, the conversations are even more candid. A series of emails between researchers at various institutions were leaked to the press in early April, nothing classified. Just internal scientific discussion that was never meant to be public. The leak revealed scientists wrestling with interpretations, sharing doubts, and occasionally expressing frustration at the constraints of what they can say publicly versus what they privately think. One email from Dr. Naomi Rowe Gurney at NASA Goddard to colleagues: "Off the record, I think we're dealing with something that doesn't fit our current taxonomic categories. Whether that means exotic natural object or artificial, I genuinely don't know. But pretending it's just a weird comet feels intellectually dishonest at this point. We need to expand our hypotheses, even if that makes administrators nervous." Another, from Dr. Henry Scher at the Planetary Science Institute: "The problem is the data is simultaneously too good and not good enough. Too good because we're seeing details we've never observed before. Anomalies that are hard to dismiss. Not good enough because we still don't have close-up imaging or direct compositional analysis. We're trying to solve a 3D puzzle with 2D shadows." The official statements tell a different story. NASA's public releases have been carefully worded masterpieces of non-commitment. A typical example from March 20th, 3I/Atlas continues to be an object of intense scientific interest. Ongoing observations are providing valuable data about the nature of interstellar objects and their interaction with the solar environment. NASA is committed to studying this object with all available resources and will share findings as analysis progresses. Notice what that statement doesn't say. It doesn't call 3I/Atlas a comet or an asteroid. It doesn't offer any explanation for the anomalies. It doesn't address the artificial hypothesis. It's pure bureaucratic neutrality, designed to sound informative while actually saying nothing. The European Space Agency has been similarly cautious. A statement from ESA's Director of Science in late March: "We are coordinating with international partners to maximize observation opportunities The unique characteristics of 3I/Atlas present exciting opportunities to advance our understanding of objects originating from beyond our solar system. Unique characteristics, exciting opportunities, code words for we don't know what we're looking at and we're trying not to freak anyone out. But here's where it gets interesting. There's a gap between what space agencies are saying publicly and what they're doing. Actions speak louder than press releases, and the actions suggest a lot more urgency than the calm public statements imply. In early April, NASA quietly redirected observation time on the James Webb Space Telescope, bumping several scheduled observations to prioritize 3I/Atlas. JWS, time is precious. Astronomers compete for years to get their projects scheduled. Changing the observation queue isn't done lightly. When asked about it, a NASA spokesperson said only schedule adjustments are routine to accommodate high-priority targets of opportunity. The National Science Foundation approved emergency funding for additional radar observations at Arecibo's successor facility in the Goldstone Deep Space Communications Complex, not through the normal grant process, which takes months. Emergency funding approved in days. The European Southern Observatory reconfigured several telescopes at its Chile facility for continuous 3Y/Atlas monitoring. Universities are cancelling classes so astronomy students can contribute to the observation effort. Amateur astronomer networks are coordinating like never before, sharing data through centralised databases. This is not routine behaviour. This is the scientific community mobilising like they're preparing for something. Dr. Frank Marcus, senior planetary astronomer at the SETI Institute, acknowledged the urgency in an interview. We're seeing a level of international cooperation and resource reallocation that I've only witnessed once before when the interstellar Comet 2I/Borisov was discovered. But even that didn't generate this intensity. There's a sense that we can't let this opportunity slip away. If 3I/Atlas leaves the solar system without us understanding it, we might regret that failure for generations. And then there are the leaks, the quiet disclosures that suggest some scientists know more than they're saying publicly, or at least suspect more than they can prove. In mid-April, an anonymous source described as a senior scientist involved in 3I/Atlas analysis told Science magazine, "There are ongoing discussions about what happens if we definitively determine this object is artificial. What are the protocols? Who makes announcements? How do we manage public reaction? These aren't theoretical conversations anymore. People are gaming out scenarios. That's remarkable. That means somewhere. In meetings we're not privy to, serious people are seriously planning for the possibility that we've detected an extraterrestrial artifact." Dr. Natalie Cabral, director of the Carl Sagan Center at the SETI Institute, went on record with a more philosophical take. Whether 3I/Atlas is natural or artificial, it's already changed something fundamental. It's forced us to confront the possibility of the other in a concrete way. This isn't hypothetical anymore. There's an object in our solar system that we don't understand, and that has profound implications for how we think about our place in the universe. But not everyone is being cautious and philosophical. Some scientists are pushing back hard against what they see as premature speculation that damages the field's credibility. Dr. Michelle Bannister. Yes. The same scientist who earlier expressed uncertainty gave a pointed interview to the BBC in which she criticised the artificial hypothesis advocates. We're letting our imaginations run wild when we should be doing rigorous science. Every anomaly we've observed has potential natural explanations that haven't been fully explored. Jumping to aliens because we don't immediately understand something is lazy thinking dressed up as open-mindedness. Dr. Jonathan McDowell, an astronomer at Harvard's Smithsonian Center for Astrophysics, was even more blunt on his blog. The problem with the artificial hypothesis is it's unfalsifiable. Any behaviour we observe can be spun as, this is what an alien probe would do. That's not science. That's storytelling. Real science proposes testable hypotheses that can be proven wrong. Show me a test that could definitively prove 3i/Atelus is natural, and we can have a scientific conversation. Until then, it's just speculation. This internal debate, passionate, sometimes heated, is playing out in academic journals, on social media and in conference calls. A draft paper submitted to Nature Astronomy arguing for serious consideration of the artificial hypothesis was rejected by peer reviewers. One review, leaked anonymously, said while the observations are intriguing, the leap to non-natural explanations is premature and not supported by the evidence presented. The authors are allowing their conclusions to outpace their data. Another paper, arguing that all of 3i/Atelus's properties could be explained by a specific type of interstellar ice composition, was also rejected for the opposite reason. The reviewers said the proposed composition requires such specific and unlikely conditions that it strains credulity. The model is tailored to fit the data rather than derived from first principles. So you have scientists criticising the artificial hypothesis as too speculative, and scientists criticising natural hypotheses as too contrived. Nobody's satisfied with the explanations on offer. Everyone agrees the data is weird. Nobody agrees on what it means. And while scientists argue, government agencies are doing something interesting, staying very, very quiet about their own analyses. NASA has a protocol for detecting technosignatures evidence of extraterrestrial technology. It's outlined in a document called the NASA Technosignatures Workshop Report from 2018. The protocol includes steps for verification, internal review, notification of international partners, and eventually public disclosure. But it's vague on timelines and who makes the final call on yes, this is artificial. When journalists asked if this protocol had been activated for 3i/Atlas, NASA's response was, we cannot comment on internal review processes. Not a denial, not a confirmation, just silence. The Pentagon's All-Domain Anomaly Resolution Office, AARO. The office that investigates UAPs, the new term for UFOs, was asked if they're involved in 3i/Atlas analysis. A spokesperson said RO's mandate covers anomalous objects in air, space and maritime domains. We are aware of 3i/Atlas and monitoring the situation, but have no comment on specific analyses. Aware of and monitoring. That's interesting phrasing. Why would an office focused on potential security threats be monitoring an astronomical object unless they thought there might be security implications? Dr. Sean Kirkpatrick, RO's former director, gave a talk at a closed-door conference in late April. No media, no recording. But attendees later reported he discussed the possibility of non-human technology in the solar system without specifically naming 3i/Atlas. Make of that what you will. What we're witnessing is a scientific community in tension, public caution masking private uncertainty, official statements saying little while actions suggest urgency, debates raging about methodology, evidence standards, and what constitutes proof in unprecedented circumstances. And threading through all of it, the awareness that this might be the most important question humans have ever faced. Are we alone? If 3i/Atlas is artificial, the answer is definitively no. If it's natural but we can't figure out how, our understanding of physics is incomplete in ways we haven't grasped. Either way, we're standing at a threshold, and the scientists tasked with figuring out which side of that threshold we're on, they're doing their best with incomplete information, professional constraints, and the weight of potentially world-changing implications, as Dr. Sarah Seeger put it in a rare moment of candour. I go back and forth daily. Some days I'm convinced it's an exotic natural object we'll eventually understand. Other days I look at the data and think, we're seeing something we were never supposed to find. The hardest part, not knowing which version, keeps me up at night. Let's zoom out for a moment, because regardless of whether 3I/Atlas is a rock, a comet, or a spacecraft, its existence forces us to grapple with questions that extend far beyond this single object. Questions about our place in the cosmos, about the prevalence of intelligence, about what it means if we're truly alone or if we're very much not alone. This isn't just astronomy anymore. This is philosophy with telescopes. Start with the most fundamental question: how common is intelligence in the universe for decades? We've tried to answer this with the Drake equation, a mathematical formula proposed by astronomer Frank Drake in 1961. It multiplies together factors like the rate of star formation, the fraction of stars with planets, the number of habitable planets per star system, and so on, all the way down to the fraction of intelligent civilizations that develop detectable technology. Plug in your estimates, do the math, and you get a number representing how many technological civilizations might exist in our galaxy right now. The problem: most of those factors are educated guesses at best, wild speculation at worst. Depending on what values you choose, the Drake equation predicts anywhere from we're alone in the galaxy to there should be millions of civilizations out there. Not exactly precise, but 3I/Atlas, if it's artificial, would give us our first hard data point. Not speculation, not probability estimates. Actual evidence that at least one other technological civilization exists or existed long enough to build interstellar probes. That single data point changes everything. Dr. Frank Drake himself, before his death in 2022, said in one of his final interviews, the discovery of even one artifact from another civilization would be the most important scientific finding in human history. It would tell us that intelligence isn't a cosmic accident, that the universe has created minds other than our own. That's profound beyond measure. And it would answer the Fermi Paradox, or at least shift it into new, equally puzzling territory. The Fermi Paradox, named after physicist Enrico Fermi, asks a simple question. If intelligent life is common in the universe, where is everybody? Our galaxy is 13.6 billion years old. It contains hundreds of billions of stars. If life emerges readily and sometimes develops intelligence and technology, the galaxy should be teeming with civilizations. Some of them should be millions of years more advanced than us. With even modest expansion rates, they should have colonized the entire galaxy by now. So where are they? Why don't we see evidence of their presence everywhere we look? Dozens of proposed solutions exist. Maybe intelligent life is extremely rare. We're one of the first. Maybe civilizations destroy themselves before they can spread. Maybe they're out there, but hiding deliberately. Maybe interstellar travel is harder than we think. Maybe advanced civilizations lose interest in expansion and just stay home. Maybe they're here, but we don't recognize the signs. If 3I/Atlas is a probe, it suddenly makes the Fermi Paradox more pointed, not less. Because okay, here's evidence that someone built interstellar probes and sent them out, but just one in billions of years, with potentially millions of civilizations. We'd expect more than one anomalous object. We'd expect the solar system to be full of them probes from countless civilizations, all exploring, all gathering data. Yet this appears to be the first we've unambiguously detected. Dr. Anders Sandberg from Oxford's Future of Humanity Institute proposed what he calls the rare probes hypothesis in a hastily written paper responding to 3I/Atlas. If interstellar probes are rare despite technological civilizations existing, what does that tell us? Perhaps interstellar travel is so difficult that even advanced civilizations rarely attempt it. Perhaps most civilizations conclude it's not worth the resource investment. Or perhaps, and this is darker, civilizations that send out probes tend not to last long enough to send many. That last possibility is chilling. What if aggressive expansionist civilizations tend to self-destruct? What if the very traits that lead to building interstellar probes, curiosity, ambition, technological prowess, correlate with traits that lead to civilizational collapse? On the flip side, if 3I/Atlas is natural and we're just seeing exotic physics we don't fully understand yet, that has its own implications. It means the universe is weirder than we thought. It means objects can form with properties we've never encountered. It means interstellar space might create conditions and materials we haven't anticipated. Dr. Gregory Laughlin from Yale University explores this in a speculative essay. Every time we've discovered something that seemed to violate our understanding, quasars, pulsars, fast radio bursts, it turned out to be natural phenomena operating under extreme conditions we hadn't previously encountered. Maybe 3I/Atlas is the same. Maybe objects that spend millions of years in interstellar space, exposed to cosmic ray bombardment and minimal heating, develop surface properties we can't replicate in laboratories. Maybe we're about to learn something fundamental about material science. But there's a third possibility that's perhaps the most unsettling of all. What if 3I/Atlas is artificial but not functional? What if it's a derelict, a dead spacecraft from a dead civilization, drifting through the galaxy like a ghost ship? Think about the timescales involved. Our own civilization has only had radio technology for about 120 years. We've only been spacefaring for about 65 years. In cosmic terms, that's a heartbeat, an eye blink. If another civilization built 3I/Atlas and launched it on an interstellar journey, how long ago did that happen? At 34 kilometers per second, covering just 50 light years would take over 440,000 years. The beings who built it could be long extinct. Their star could have gone supernova. Their entire civilization could have risen, flourished, and fallen to dust while their probe silently coasted through the void. We might be looking at an archaeological artifact from a species that died out before the first humans walked on Earth. Dr. Caleb Scharf from Columbia University explores this melancholy possibility. We imagine first contact as meeting living aliens, communicating, exchanging ideas. But the universe is vast and old. The more likely scenario for first contact might be finding remnants, ruins, artifacts, messages in bottles sent by civilizations that are now gone. If 3I/Atlas is artificial, it might be the loneliest object in the solar system, a machine still following its programming long after its creators ceased to exist. That raises profound questions about our own legacy. Right now, we have 5 probes on interstellar trajectories. Voyager 1 carries a golden record with sounds and images from Earth music, greetings in multiple languages, pictures of humans and our world. It's designed to last billions of years, drifting through space long after Earth itself might be gone. What if 3I/Atlas carries something similar? What if somewhere on or in that object is a message, a record, a greeting from minds we'll never meet? The thought is simultaneously thrilling and heartbreaking. But let's consider the implications if 3I/Atlas is still functional, still actively exploring. That means we're under observation right now. Something is watching us, studying us, collecting data about our world, our civilization, perhaps even our biology and behavior. How does that feel for some people? It's exciting, the ultimate validation that we're not alone, that we matter to someone else in the universe. For others, it's deeply unsettling. We're used to being the observers, The scientists, the ones doing the studying, being the subject of study, the specimens under the microscope, flips that relationship in uncomfortable ways. Dr. Catherine Denning, an anthropologist who studies the societal implications of contact with extraterrestrial intelligence, wrote, "If 3I/Atlas is an active probe, humanity needs to grapple with the fact that we're being examined by an intelligence whose motives, ethics, and intentions we cannot fathom. Are we being evaluated, catalogued, judged? We project human frameworks onto this scenario, but truly alien intelligence might operate under completely different values and goals. What would an extraterrestrial civilization want to know about us? Are they mapping habitable worlds, searching for life, specifically looking for intelligent species? Are we interesting to them, or just another data point in a billion-year survey of the galaxy? And here's an even stranger thought. What if they already know about us? What if 3I/Atlas arrived here decades or centuries ago, has been quietly orbiting in the outer solar system, and only recently moved inward because we achieved some threshold of technological development that made us interesting? What if it came to check us out specifically? That's pure speculation, of course, but it's speculation that serious researchers are quietly entertaining in private conversations, even if they won't say it publicly. The implications extend to how we think about our future. If technological civilizations exist and build interstellar probes, that means interstellar travel, or at least interstellar communication via proxy, is achievable. It means the dream of reaching other stars isn't just science fiction. It's a path other beings have walked before us, which means we might walk it too someday. Dr. Mae Jemison, former astronaut and current leader of the 100-year Starship project, sees hope in that if 3I/Atlas is artificial, it proves that civilizations can master interstellar distances. That's encouraging. It means the challenges we face, propulsion, longevity, navigation, are solvable. Someone solved them. That means we can too. But it also means we're not special. We're not unique. We're not the chosen ones. The universe is only conscious observers. We're just one species among potentially many. One voice in a chorus we've only just begun to hear. For some people, that's liberating a relief from the burden of cosmic loneliness. For others, it's deflating. If intelligence is common, if civilizations rise and fall throughout the galaxy, then maybe we don't matter as much as we thought. Dr. David Grinspoon, an astrobiologist, offers a different perspective. Finding evidence of other intelligence doesn't diminish our significance. If anything, it increases our responsibility. It means we're part of a larger community of minds, even if separated by vast distances and time. It means our actions matter not just to us, but in the context of a universe that creates and sustains intelligence. We're not alone in pondering existence, and that's beautiful, not diminishing. So where does that leave us? Contemplating 3I/Atlas as it continues its journey through our solar system, waiting for more data? Certainly. Hoping for answers? Definitely. But also wrestling with questions that go far beyond what is this object, and into the realm of who are we, and what does our existence mean in a universe that might be full of minds like ours. The next few months will bring more observations, more analysis, possibly even a close flyby mission if NASA can pull it off. We'll learn more about 3I/Atlas's composition, structure, and behaviour. We might get answers, or we might just get more questions. But whatever we discover, the conversation has already changed. We've already crossed a threshold simply by finding an object that makes us ask these questions seriously. And in a way, that might be 3I/Atlas's most important legacy, not what it is, but what it makes us think about. As Carl Sagan once said, the cosmos is within us. We are made of star stuff. We are a way for the universe to know itself. If 3i/Atlas is artificial, the universe has found at least 2 ways to know itself. And that changes everything. So here we are, early May 2025. 3i/Atlas is making its way back out toward the edges of the solar system, having passed through the inner reaches and survived everything the sun threw at it. The object that defied physics, or at least defied our understanding of it, is slipping away, and the clock is ticking. Right now, 3i/Atlas is approximately 180 million miles from Earth, about the distance to Mars at its farthest. It's still observable, but getting harder to study with each passing day. As it moves farther from the sun, it receives less light, which means it appears dimmer to our telescopes. The window for detailed observation is closing, and everyone knows it. NASA's Jet Propulsion Laboratory is working around the clock on a mission proposal. The concept is audacious, a fast-track spacecraft launched on a SpaceX Falcon Heavy, using a gravity assist from Venus to catch up with 3i/Atlas sometime in late 2025 or early 2026. The probe would carry cameras for high-resolution imaging, spectrometers for compositional analysis, a magnetometer to detect any magnetic fields, and radar to penetrate the surface and map internal structure. Dr. Dina Prialnik, leading the mission design team, briefed Congress on the proposal. This is our one shot. If we don't launch within the next 2 to 3 months, the trajectory becomes impossible with current propulsion technology. We'll have to watch 3i/Atlas leave the solar system without ever getting close enough to truly understand it. That would be a failure we'd regret for generations. The estimated cost, about $780 million for a bare-bones mission. That's cheap by space exploration standards. The James Webb Space Telescope cost $10 billion. But it still requires emergency funding approval, international cooperation, and accepting higher risks than NASA normally tolerates. Fast missions mean less testing, less redundancy, more chances for something to go wrong. Congress is debating. The House Science Committee held hearings in late April. Some representatives argued it's essential. How can we not investigate what might be the most important discovery in history? Others worried about costs, technical feasibility, and what happens if the mission fails and we've spent $750 million to watch a spacecraft miss its target. Representative Jim Baird from Indiana asked the question everyone was thinking: what if we get there and it's just a rock? An unusual rock, sure, but a rock nonetheless. How do we justify that expense to taxpayers? Dr. Thomas Zurbuchen, former NASA Associate Administrator, answered, "If it's just a rock, we'll learn something unprecedented about material science and interstellar object formation. If it's more than a rock, and the data suggests it might be, we'll have made contact with evidence of extraterrestrial technology. Either outcome justifies the investment. The only inexcusable choice is doing nothing." Meanwhile, the European Space Agency is exploring a complementary mission, a high-powered laser communication attempt. The idea is simple but profound. If 3i/Atlas is artificial and still functional, it might respond to a signal. ESA proposes using ground-based lasers to pulse a mathematical sequence, prime numbers, the Fibonacci sequence, geometric proofs, something that unmistakably indicates intelligence. Dr. Claudio Maccone, technical director at the International Academy of Astronautics, explained the rationale. If 3i/Atlas is a probe designed for exploration, it would likely have programming to recognize and respond to deliberate signals. We're not trying to decode alien language or philosophy. We're just saying we're here, we're intelligent, and we see you. If it responds, we have our answer. The proposal has critics. Some scientists worry about the implications of actively signaling an object we don't understand. We don't know what we're dealing with, argued Dr. John Gertz from the SETI Institute. Shouting into the dark before we know who's listening is potentially dangerous. We should observe and analyse before we announce our presence. But others point out that any sufficiently advanced probe would have already detected us. Our radio and television broadcasts have been leaking into space for a century. Our civilization is hardly hidden. We've already announced ourselves, countered Dr. Seth Shostak, also from SETI. Every time someone turns on a radio transmitter, we're sending a signal into space. Worrying about a targeted laser transmission when we've been inadvertently broadcasting for decades is like worrying about lighting a candle after setting off fireworks. As these debates rage, the observations continue. Every major observatory on Earth is still tracking 3/Atlas when it's visible. The data keeps accumulating, and with it, the mystery deepens rather than resolves. In late April, Hubble captured images showing something new, a very faint, asymmetric haze around 3/Atlas. Not a tail like a comet would have, not symmetric like you'd expect from outgassing, just a slight lopsided glow, Dr. Jessica Sunshine from the University of Maryland analysed the images. It's as if something vented briefly from one side of the object, but spectroscopy shows no volatiles, no gas emission. I don't know what created this haze. Dust knocked off the surface by a micrometeorite impact, some kind of deliberate discharge. We're speculating without data. The rotational period has also changed slightly. After months of perfect stability, the 8.7-hour rotation has shifted to 8.69 hours, a tiny difference, barely outside measurement error. But if real, it's significant. Something altered its angular momentum, noted Dr. Peter Pravec from the Astronomical Institute in the Czech Republic, either through internal mass redistribution or external torque. For a natural object, this could be explained by outgassing or impact. For an artificial object, it could indicate systems activity, reaction wheels adjusting, internal components moving, something. Then there's the trajectory refinement that was detected in early May. 3/Atlas made another small course correction about 15 kilometres deviation from the predicted path, then a gradual drift back. This is the third such correction observed. The pattern is now undeniable, whatever's causing these deviations. It's not random, it's not measurement error. Something is altering 3/Atlas's trajectory in small, periodic ways. If I saw this behaviour in an asteroid, I'd attribute it to outgassing producing non-gravitational acceleration, said Dr. Davida Farnokia. But we're not detecting outgassing, so either there's gas emission below our detection threshold, which seems unlikely given how sensitive our instruments are, or something else is producing thrust. I don't have a natural explanation that fits all the data anymore. Amateur astronomers have become crucial to the observation effort, with thousands of telescopes pointed at 3/Atlas. They're providing near-continuous coverage. A network called the Interstellar Object Observers Coalition, IOOC, formed specifically to track 3/Atlas, has members in 47 countries. They share data in real time, creating a distributed observation network that rivals professional facilities. One amateur astronomer, Roberto Martinez from Argentina, captured something odd on May 3rd, a brief brightening, lasting about 12 minutes, that corresponded with 3/Atlas passing through the plane of the solar system's magnetic field. Professional observatories confirmed it. The object brightened by about 0.2 magnitudes, then returned to baseline. That's not random, Martinez told a science podcast. It happened precisely when the object crossed a specific location in space. Either that's the most incredible coincidence, or 3/Atlas is responding to its environment in ways natural objects don't. As 3i/Atlas continues its outbound journey, speculation has reached fever pitch. Social media is ablaze. Reddit's r/3iAtlas has 2.3 million members. YouTube videos analysing every piece of data rack up millions of views. Documentaries are in production. Books are being written, you're probably listening to one right now. But beyond the media frenzy, beyond the scientific debates, there's a quieter realisation spreading through the astronomy community we might never get definitive answers. 3i/Atlas might leave the solar system still wrapped in mystery, an enigma that visited us briefly and departed, leaving only questions in its wake. Dr. Alan Stern, principal investigator of the New Horizons mission that flew by Pluto, put it starkly. We had decades to prepare for Pluto. We had years to prepare for Arakoth. With interstellar objects, we get weeks or months of warning, and they're moving too fast to catch with conventional missions. Unless we have spacecraft already deployed and waiting, or unless we develop dramatically faster propulsion, these visitors will always be ghosts seen briefly, studied inadequately, gone before we can truly know them. That's the frustration. That's the tragedy. We might be looking at the most important object ever to enter our solar system, and we might not be able to do anything more than watch it leave. But there's still hope. The mission proposal is alive. The funding debates continue. Engineers are working on contingency plans, backup trajectories, creative solutions. If there's one thing humans are good at, it's solving problems when we're motivated. And right now, we're very motivated. As of today, mid-May 2025, 3i/Atlas is 210 million miles from Earth and counting. Every day, it gets harder to observe. Every week, the launch window for an intercept mission narrows. The countdown has begun, not in the dramatic way of the solar storm approach, but in the slow, inevitable way of an opportunity slipping through our fingers. Will we catch it? Will we learn its secrets before it's gone? Or will 3i/Atlas join Oumuamua as an interstellar object that challenged everything we thought we knew, and left us wondering? The answer depends on decisions being made right now, in government offices and scientific institutions, in funding committees and engineering labs. The universe has given us a gift, a visitor from the stars, something to study, something to puzzle over, something to remind us that we're part of a cosmos far stranger and more wonderful than we sometimes remember. What we do with that gift is up to us. The clock is ticking. 3i/Atlas is leaving. And the question hanging over all of us, scientist and civilian alike, is simple but profound. Will we be able to say we did everything we could to understand it? Or will we spend the rest of our lives wondering what we missed? The chase is still on. The mystery remains unsolved. And somewhere out there, a small object no bigger than a few city blocks is carrying secrets through the darkness, secrets we might never learn, or secrets that might change everything we think we know about our place in the universe. Your move, humanity,